all, the topic that we are going to see now is the smart antennas. So coming to the outline of this presentation, we are first going to see the definition of smart antennas, then the basic introduction about how to achieve smart antennas, and finally the construction and working of smart antennas. Now, starting with the definition of a smart antenna. When can we make an antenna to be smart? When can we make an antenna array to be smart? So we call an antenna array to be smart antenna when it is capable of directing the desired signal in a proper direction and directing the null towards the undesired direction. Null means the unwanted side lobes and minor lobes. So when an array is capable of doing such a process where it is directing its main beam towards the desired signal and null towards an undesired direction, we call the antennas to be smart in nature. And also, the smart antennas are called as adaptive arrays, which are capable of maximizing or increasing its signal to noise ratio. Coming to the introduction of the antenna arrays, the adaptive antennas, we can enhance the performance of this smart antennas by using certain digital processing techniques. So when we employ the methods of sampling and digitization of the signals at the terminals of the antennas, we can try to achieve a high efficiency, good signal. And this, when processed through a computer, we can actually build a very smart antenna in principle. And since it follows the principles of sampling and digitization, these antennas are also called as digital beamforming antennas. Coming to the construction and working of the smart antennas, this is the diagram that represents a smart antenna. So we are considering two dipole antennas which are placed at a distance of lambda by 2 from each other. So my dipole 1 is placed here, my dipole 2 is placed at a distance of lambda by 2 from dipole 1. Now, we are going to consider a signal that is incident on dipole 1. So this is your incoming signal direction, and this makes an angle of 30 degrees from the broadside. So this is your antenna. This is the direction of the maximum. So this is your broadside. So the incoming signal makes an angle of 30 degrees with the broadside. Now when you observe this diagram, this signal is incident on dipole 1. If this has to reach dipole 2, it has to travel an additional distance of lambda by 4. So the distance between the original signal reaches the dipole 1, but if the same signal has to reach dipole 2, this will travel an additional distance of lambda by 4, which is nothing but it gets retarded by a phase of 90 degree in this particular dipole 2. Now if you observe the diagram, we can see that both dipole 1 and dipole 2, each of them have their own mixer. So dipole 1 has its mixer, dipole 2 has its mixer. They have their own voltage control oscillators, which are represented by VCO. They have their own intermediate frequency amplifier, which is represented as IF amplifier. And also they have a phase detector, which is represented by the phi symbol. So each of the antennas are equipped with these kind of equipments. Now what will happen? We know that the signal incident on dipole 1 and signal incident on dipole 2 have different phases. When the phases are different, the output voltage that we get will be lesser. Like since they're out of phase, they get subtracted and we get a lesser voltage. So what we must try to do is apply the voltage that we have received, the phase of the incoming signal, it is compared to the phase of this reference oscillator. So for example, we said that this has an angle of 30 degree and dipole 2 is retarded by a 90 degree. What this IF reference oscillator will do, it will compare the phase of the downshifted signal with the phase of this reference oscillator. Based on the phase difference, a voltage will be produced, and this voltage will increase or reduce the phase based on the requirement, such that the phase difference between the signals becomes 0. I repeat once again, this IF reference oscillator, it will compare the phase of the downshifted signal with the phase of the reference oscillator, and it will produce a voltage that is proportional to the phase difference. What is the function of this voltage? This voltage is going to either increase the phase or decrease the phase of the obtained signal, so that the phase difference becomes totally 0. Now what will happen when the phase becomes totally 0? We can say that the phase of signal 1 phi 1 is equal to phase of signal 2, which is phi 2, which is equal to phi naught, which is the phase of your reference oscillator. And when the phases are equal, also from this IF amplifier we get voltage outputs of equal gain. So V1 will be equal to V2. The voltage received at this first antenna will be equal to the voltage received at the second antenna. So what will happen? Both the voltages get summed up and we get the output voltage which is twice of the required voltage value. So this is V1. V2 is also the same value of V1. So V1 plus V1 becomes 2 times of V1 or 2 times of V2 since V1 and V2 are the same. This will maximize the response of the array to the incoming signal, and therefore what happens? It will steer the beam towards your required direction. So this is the working of the smart antennas, where we keep on comparing the phase difference. We produce a voltage in proportional to the phase. We make the phase back. We either advance it or retard it such that the phase difference is 0. And when we add up the total voltage values after minimizing the phase difference, we get the total output voltage to be twice that of your original voltage value. So this actually maximizes the antenna performance, and this is helpful in steering the beam onto your incoming signal. This is all about smart antennas.